Pascal's triangle. Known in India as the staircase of Mount Meru, Khayyam's triangle in Iran, and Yang-Wei's triangle in China, it is actually credited to French mathematician and physicist of the 17th century, whose name is Blaise Pascal, after whom the triangle is named. It is infinite, endless, and has so many secrets involved. Let us delve into some of the beautiful patterns and secrets that the Pascal's triangles tell us. First diagonals, 1 on both sides. If we look carefully at the Pascal's triangle, we can notice that the first diagonal from both the right side and the left side have 1. No matter how huge the triangle is, 1 will always be on both ends. And in the second diagonals, we have counting or natural numbers. If we look closely on both right and left side, we can see that the counting numbers or natural numbers, that is 1, 2, 3, and so on, are highlighted here. And they remain the same no matter how huge a triangle we take. In the third diagonals, we have triangular numbers. The first diagonal had the number 1, while the second diagonals had the counting or natural numbers. And the third diagonals have a special sequence of numbers, which goes as follows: 1, 3, 6, 10, 15, 21, 28, and so on. These numbers are called triangular numbers because if we arrange these numbers in the form of 1 plus 2 plus 3, that is the sum of natural numbers, we will get these numbers, that is 3, 6, 10, 15, etc., where 3 is the sum of 1 plus 2, 6 is the sum of 1 plus 2 plus 3, and so on. Further, if we take as many dots as these numbers, we will be able to arrange them into an equilateral triangle. The four diagonals showcase tetrahedral numbers. If I take a triangle which has 3 sides, and from each of its sides I draw another triangle, it will form a net which can be folded in this manner to form a 3D shape known as a tetrahedron, which is also called a triangular pyramid. A tetrahedron is composed of 4 triangular faces, 6 straight edges, and 4 vertex corners. If I take as many spheres, so as the numbers which are given here that are highlighted in yellow, then I will be able to form them into an equilateral tetrahedron, which means all the sides of the tetrahedron will be equal in length. So here are the numbers 1, 4, 10, 20, 35, 56, 84, etc., which are showcased on both the right and left diagonals from the fourth. Another amazing feature of the Pascal's triangle is that it is symmetrical. So if we take it and fold it into half, then both sides will exactly overlap each other. Powers of 2. If I take a look at the Pascal's triangle and add up the numbers present in each row, I will be able to observe a unique pattern. The second row gives 2, the third 4, then 8, 16, 32, 64, and so on. We can say that the numbers are doubling, but more efficiently, we can say that these are all the powers of 2, where 2 can be expressed as 2 power 1, 4 as 2 squared, 8 as a cubed, 16 as 2 raised to 4, and so on. Powers of 11. Last time, I added the values in each row. For example, in the second row, I did 1 plus 1, and so on. But now, I will simply put these digits together. For example, in the second row, instead of adding 1 and 1, I will simply take 1 and 1 together and write it as 11. This 11 can be written as 11 raised to 1. Now let us find the connection as to why we are writing 11 raised to 1. because the next row will give me 121, which is 11 squared. Following it is 1331, which is 11 cubed. And then we have 14641, which is 11 raised to 4. This gives a very simple method of finding the powers of 11. However, what do we do from the fifth row onwards? Here we have to add the numbers from a right to left direction. We will write the first number, that is first digit from the right, which is 1, then 5. And since here we have a 2-digit number, we will write the single digit as it is and add the tens digit with the ones digit of the next number. So 1 plus 0 will give us 1. We will follow suit for the remaining. 5 plus 1 is 6. And since 1 is already in its ones place, we will write it as it is. And rightly enough, if I check what is 11 raised to 5, I will get 161051. Isn't that amazing? And similarly, if I go for the next row as well, I will get 1771561, which is 11 raised to 6. Now let us move on to the next property of the Pascal's triangle. Squares. Let me highlight the second diagonals from both sides in the Pascal's triangle. As we have already done, we know that these diagonals give us the counting on natural numbers. It is very interesting to notice that the squares of these highlighted numbers are the sum of the numbers rightly to its right and the number exactly below these two numbers. Let me give you an example. For example, if I take the number 2, which square is 4, then I will find that 4 is the sum of the number to the right of 2, that is 1, and the number below these two numbers, that is 3. And rightly said, 3 plus 1 gives me 4. Similarly, 3 square is 9, which is a sum of 3 and 6. Isn't that amazing? Now let us move on to find out about odd and even magic inside the Pascal's triangle. Can you see this beautiful design? What exactly have I done here? All I have done is highlighted the even numbers 2, 4, 6, 10, 20, and so on. Only thing that has been done here is that the even numbers have been highlighted, and it gives us a beautiful triangular sort of pattern. This pattern is known as the Sierpinski Triangle, which is a self-similar fractal that consists of an equilateral triangle with smaller equilateral triangles recursively removed from its remaining area. For example, I have an equilateral triangle here. In the remaining space, I cut an inverted equilateral triangle, which gives me 3 remaining black equilateral triangles, where I cut 3 more inverted equilateral triangles. And this goes on with the remaining space to give us a beautiful design, similar to what we observed in the previous slide. The most useful part of the Pascal's triangle is that it helps us find the binomial expansion of any binomial. Before we go to that, let us know what the binomial theorem is. The binomial theorem tells us how to expand expressions of the form a plus b raised to n. For example, x plus y raised to 7. Pascal's triangle gives the coefficients for an expanded binomial of the form a plus b raised to n, where n is the row of the triangle. The binomial theorem tells us we can use these coefficients to find the entire expanded binomial. For example, if I take the following binomial a plus b and take the second row of the Pascal's triangle and put 2 as its power, then I will be able to expand it into the identity a square plus 2ab plus b square. Now we know that the coefficient of a square is 1, since nothing else is mentioned here, 2 for 2ab, and again 1 for b square. which gives us 1, 2, and 1. If we look closely, this has been observed somewhere else. Exactly. If we go behind and look at the Pascal's triangle, the second row gives us 121. In the similar manner, if we take a plus b the whole cube, we will get a cube plus 3a square b plus 3ab square plus b cube, where the coefficients are 1, 3, 3, and 1, which comes in the fourth row of the Pascal's triangle. Until now, we have been referring as 1, 2, 3, and so on for the rows of the Pascal's triangle. But after learning this concept, we can conclude that the rows are instead named from 0 onwards, where the one at the top will be the 0th row, and the row below it will be the first row, then the second row, and so on. And that is how, when we expanded a plus b the whole square, square is the number of the row, and that is how we got 1 to 1 as the coefficients. Thank you so much and have a wonderful day ahead.